We'll explore context engineering in healthcare, applying a structured framework to clinical document processing AI designed to progress step by step from minimal viable product through to production readiness. Let's imagine we're building an AI system that helps doctors and coders process clinical notes. The problem we resolve is that a model analyzing patient notes sometimes overlooks important details or mixes up time-sensitive information. How do we design the context so the AI is safe, accurate, and actually useful? We'll walk through it step by step. First of all, define a narrow starting point. Don't try to solve everything at once. For example, start with extracting medications and allergies from discharge summaries or generating ICD-10 codes from outpatient notes. Then decide what success looks like. That might be catching over 90% of medications correctly or cutting down coding rework by 20%. Step 1. Handle privacy and governance. Since we're working with patient data, the first thing is security. Notes should be encrypted, only accessible to the right people, and fully auditable. And the AI's outputs must be reviewed by a human. No auto sign-off. Step 2. Normalize the input. Doctors write notes in very different ways, so we want to organize information into a standard shape. For healthcare, that means mapping things into FHIR resources. So a medication is always a medication object. A diagnosis is always a condition object, and so on. We also normalize units, dates, and medical terms. Step 3. Bring in reliable knowledge. The AI shouldn't just guess. It needs to reference clinical guidelines, hospital policies, and coding standards, so we keep these documents in a database and allow the AI to pull in the right ones depending on the task. For example, if we're coding diabetes care, it should fetch diabetes guidelines. Step 4. Structure the context packet. Now comes the heart of context engineering, deciding exactly what the AI sees when we call it. Instead of dumping the whole patient chart, we package the information. At the top, we set the role. You are a clinical documentation assistant. Then we give a patient snapshot: age, sex, allergies, active medications. After that, a timeline of recent visits or events. Then the source document we're analyzing, like today's progress note. Finally, any guidelines or rules we want the AI to follow. This packet gives the AI just enough to work with, structured, concise, and safe. Step 5. Define prompts and constraints. We then tell the AI very clearly what to do. For example, extract all medications into JSON format or summarize the HPI section in 120 words. We also set constraints. Do not invent diagnoses. If unsure, say uncertain. Cite the guideline ID if you use one. Step 6. Adapt context depending on the task. Sometimes we want a summarizer, sometimes an extractor, sometimes a coder. So we build different templates for each role. And if the note is huge, we trim it down to the most relevant sections, like just the last 90 days of history. Step 7. Add guardrails. We don't just trust the AI blindly. After it responds, we validate its output. For example, does the medication dose fall within safe ranges? Does the recommendation match the guideline it cited? If there's a conflict, like 2 different insulin doses, we flag it for human review. Step 8. Keep the human in the loop. Doctors or coders should see the AI's output side by side with the original text. If the AI says penicillin allergy rash, the human should be able to click and see exactly where in the note that came from. They can accept, reject, or edit. That feedback improves the system over time. Step 9. Evaluate carefully. We don't just measure whether the AI sounds good. We measure precision and recall on actual data sets like Mimic or I2B2. And in real clinics, we measure outcomes like time saved or error reduction. Step 10. Monitor in production. Over time, guidelines change and hospital policies get updated, so we need monitoring, tracking which guidelines the AI is using, how often it abstains, and whether errors creep in. Step 11, minimal viable pipeline. Now let's put all of this together into a simple pipeline you can actually implement today. Think of it as the smallest working version of your healthcare AI. First, pre-processing. We start by ingesting a clinical note and tagging its sections. Things like history of present illness, review of systems, medications, allergies, and labs. We also clean and normalize what's inside. For example, making sure units are consistent and mapping anything structured, like medications, into the FHIR format. From this, we build a patient snapshot plus a 90-day timeline of recent history. Second, retrieval. We pull in external knowledge. Using the patient's specialty, their main problem, their location, and the date, we query our guideline library. From there, we retrieve the top 4 most relevant chunks along with their IDs. Third, assembling the packet. With all that in place, we assemble the context packet. This is the carefully structured input that the AI will see: patient snapshot, recent timeline, today's note, and the guideline snippets. We keep it concise, ideally under 4,000 to 6,000 tokens. Fourth, execution. Then we run the task template. For example, if our job is extracting medications, we pass the packet through the extractor template. The AI responds with structured FHIR JSON, strictly following the schema. Finally, validation and presentation. Before showing it to the clinician, we run some rule-based checks. We confirm doses make sense, check for contradictions, and flag anything suspicious. Then we present the results side by side with the source text with provenance highlights. The clinician can accept, edit, or reject, and that feedback closes the loop. Here are the examples of output schema and summarization template. That's the minimal viable pipeline: pre-process, retrieve, assemble, execute, and validate. It's the fastest path to a working healthcare AI that's safe, structured, and clinically useful. Step 12, grow gradually. Finally, we roll out in phases. First, a simple medication extraction tool. Next, summaries and coding support. Later, full specialty-specific packs like cardiology or oncology. Each stage builds on the last.